Let's continue with 3.1 examples. So for question 7, we rewrite each of the following statements without using quantifier symbols. So we have here, for all x that belongs to R, x squared plus 1 is bigger than 0. So this will be every real number a square and added 1 is bigger than 0. For B, we have a cis n that belongs to the integers, so that n squared is equals n. So you will write here, there is an integer so that its square is equals to the number. C, you have for all students in Math 1071, S has a student ID or ID number. So you will say like every student in Math 1071 has a ID number. ID student number. All right. Now, for number 8, we're trying to determine the truth value of each of these universal conditional statements and give a counterexample if this is not true. So we have for all x that belongs to R, if x is bigger than 5, then x is bigger than 3. This, of course, is going to be true. In general, you can see that if something is bigger than 5, because of the position on the real line, that something is going to be bigger than 3. Okay, so this is true. Now, for all n that belongs to the integers, if n is even, then n squared is even. This is something that you can actually kind of prove. If you say that something is even, it's because it's twice another integer. Okay, so this will be a representation of even. And when you do n squared, you're going to get this is 4k squared, which you can see as twice 2k squared or twice some number s. So actually n squared is even too. So this will be true. And C says for all x that belongs to the real numbers, if x squared is equals 4, then x is equals 2. And this is actually false because it says x equals minus 2, so that x squared is 4. And it's not 2. So there we have our counter example for this one. Now, for question number 9, it says consider the statement for all n that belongs to the integers. If n is divisible by 6, then n is divisible by 2. Is this true? Yeah, this is actually going to be true. Remember, if n is divisible by 6, it means that n is 6 times some other integer, right? But this means that this is twice 3 times k. And I can just call this 3 times k s. So it's going to be, since n is twice s, then n is divisible by 2. It says write this using the imply notation. So the way that you will write this is for all n that belongs to the integers, if n is divisible by 6, so if n is divisible by 6 with that notation, then 2 n is divisible by 2. Or yeah, you can also use divisible by 6 in here to replace this. Give an example that illustrate that statement. For example, if I give n equals 12. So n equals 12 is divisible by 6. As 12 can be seen as 6 times 2. But it also divisible by 2. As 12 can be seen as 2 by 6. So you can see here that that will make it divisible by 2. Now 10. Find the truth set for p of x equal x squared minus x with domain integers, real numbers, and a particular domain in there. So if we're going for real numbers, we're essentially looking for the solutions to this. We can factor this out. This is x minus 3, x plus 2 equals 0. And this will give me solutions x equals 3, x equals minus 2. They're both integers solutions. So the truth set for this case is minus 2, 3, which will make that 0. On the real numbers, they're the same, in particular because this is a quadratic. It's going to have 2 solutions. So the truth set is the same for both. Now, when we're looking on this specific domain, notice that minus 2 is included there. 3 is also included there. So it's also the minus 2, 3 domain. Okay. So in all 3 domains, it happens to be the same, but perfectly, if I just restrict this domain, maybe I'll just get one of the solutions. It's not always going to be the case. Now, determine whether the following statement is true or false. If x squared is equals 9, then x is equals 3. This is false. And we already saw the counterexample. This is very similar to before. X equals minus 3 is going to produce x squared equals 9, but x is different from 3. Okay. Number 12, we have 2, 3, 4, 5. Consider p of x be the predicate x is prime. So let's find the truth set of p of x. Well, the primes here of this will be 2, 3, and 5. Since 2, 3, and 5 are the prime numbers. For all x that belongs to D, p of x is true or false. Well, the answer is false because 4 doesn't work. Four is not prime. Now, is this an x that belongs to D such that p of x is true? Yeah, this is true. 2, 3, 5 are going to work out. 4 doesn't work out, and so that voids the for all. But when we're talking about an exists, we just need one single number. So any of these 3 numbers is going to work out. All right, let's move on to question 13. So it says, write a predicate p of x with domain C such that the truth set is minus 2, 1, 0, 2. In particular, I can go with p of x be the predicate x less or equals than 2 with x that belongs to the integers. And that's going to work, of course, because this is describing exactly that set is the number between minus 2 and 2 that belongs to the integers. Now, for all x that belongs to C, is p of x true? No, this is false. Because I can take any number that is outside of this set, and it's not going to work out. So x equals 3. 3 has bigger absolute value than 2. Now, for all x that belongs to C, p of x is false. Now, this is also false because we do have examples. So x equals 0 has absolute value of 0 being 0, which is less or equals than 2. So this particular predicate doesn't necessarily have to be true for everything or false for everything. Now 14. Here we have for all x that belongs to R, x squared is bigger than 0. And we have a second predicate that is, it says x that belongs to R such that x squared is bigger than 0. It says which is stronger and which is easier to prove. Well, the for all is always going to be stronger, since this is telling me for all numbers. So it's a much stronger statement. The for all is always much more stronger than the SS. The SS, however, is going to be much more easier to prove. So this is easier to prove because you just need to show one example. So as an example, x equals 0, then x squared is going to be bigger or equal than 0. Because in particular, x squared is equal to 0 in this scenario. So with this, I just proved this statement. Now to prove this one is much more complicated. Okay. All right. So this is the end of 3.1 examples.